In this session, we are going to study another special functions, Legendre functions. Legendre function is a solution of Legendre's equations. As I explained, Legendre's equations is expressed 1 minus x squared y2 prime minus 2xy prime plus n plus 1 y equals 0. Then we'd like to find out the solutions around x equals 0. If you look at this equation, you can easily find x equals 0 is an ordinary point. And also you can recognize from these equations, x equals plus minus 1 is a singular point. The solutions is applied x is minus 1 to the 1s. This is a range of the x when you solve these equations. X equals 0 is an ordinary point. We'd like to expand the power series solutions around x equals 0 following these equations, power series. You can find out the y primes and the y2 primes. Then substitute into the y2 primes and the y primes into these equations. Equation becomes the next lines. When you substitute I equals 0, you have a constant value terms. And the next one is I equals 1's coefficient times x. Then next term is x squared, x cubed. It's starting from the I equals 2 to the infinities. This is a coefficient. Even if you substitute any value of the x, this have to be 0. So every coefficient need to be 0 to satisfy these equations. You have 3 equations. Coefficient of the constant value is n times n plus 1 c sub 0 plus 2 c sub 2 equals 0. The coefficient of the x is the next equation, n minus 1 times n plus 2 times c sub 1 plus 6 c sub 3 equals 0. The coefficient of the x to the I, the third equation we obtained. So we have these 3 equations. From the first equation, you can write c sub 2 equals minus n times n plus 1 over 2 c sub 0. From the second equation, you have an expression for the c sub 3 equal negative n minus 1 n plus 2 over 6 c sub 1s. So we have found the relation between the c sub 0 and the c sub 2 and the c sub 1 and the c sub 3s. If you want to find out the relation between the c sub 2 and the c sub 4 or c sub 5 to the c sub 3s, you can use a third equation. Third equation, c sub I plus 2 equal negative n minus I, n plus I plus 1 over I plus 2, I plus 1 times c sub I. So using the third equation, you can keep finding the c sub 4 and the c sub 5, c sub 6, c sub 7 using these equations. We obtained the 2 independent solutions of the Legendre equation is given by these equations. One of the function y sub 1 is c sub 0 times so this is corresponds to c sub 2. This corresponds to c sub 4. And this corresponds to c sub 6. So we can keep calculating c sub 8 and c sub 10 following the same method. And the function y sub 2 expressed as a multiple of the c sub 1s. So c sub 1 times x, and this is c sub 3. This is c sub 5. This is c sub 7. If you don't consider the specific value of n. But if you look at the expressions what's happened when for example, if you choose n equal 4, this n minus 4 becomes 0. So if you choose n equal 4, equations of the y sub 1 is terminate up to the third terms. You need to consider the third terms, and from the fourth terms, all terms becomes 0. So y sub 1 cannot become the infinite series. Instead, it becomes polynomials. If we consider n equal 4, this becomes 0. And if you consider the n equal 5, these terms n minus 5 becomes 0. If you consider n equal 5. If you consider the odd number of n, y sub 2 becomes the polynomials. But if you consider the n equal 4, y sub 1 becomes a polynomial, but y sub 2 is an infinite series. If you consider the n equal 5 odd numbers, y sub 2 becomes a polynomials, but y sub 1 is an infinite series. So for even integers, y sub 1 is a polynomials, y sub 2 is an infinite series, but for the odd integer n, y sub 2 is a polynomials, whereas y sub 1 is an infinite series. I'd like to introduce Legendre polynomials. We have to choose the c sub 0 and c sub 1. For the n equals 0, c sub 0 is 1. We can determine the c sub 0 as you like. This is a conventional choice for the c sub 0 and c sub 1. So for the n equal 1, c sub 1 is equal to the 1. For the even integers for n, we choose the c sub 0 is a negative 1 to the n over 2 times 1 times 3 times blah 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 up to the n minus 1. N minus 1 is a odd numbers when the n is a even numbers. Over 2 times 4 times blah 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 up to the n. For the odd number of n except n equal 1, c sub 1 is determined this way. Negative 1 to the n minus 1 over 2 times 1 times 3 times blah 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 up to the n. N is odd numbers over 2 times 4 times blah 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 up to the n minus 1. N minus 1 is even numbers. In the case of the n is odd numbers. Using this definition of the c sub 0 and c sub 1, we introduce the Legendre polynomial. This is the solutions of the Legendre's equations. The solution is expressed with the Legendre polynomials. Capital P sub 0 is a y sub 1x in the case of the n equals 0. That's a 1. P sub 1 is a y sub 2x, n equal 1. This is x. When the P sub 2x is we choose a y sub 1, n equal 2. Then the polynomial is expressed 1 over 2 times 3x squared minus 1. P sub 3 is we choose a y sub 2, n equals 3. And the polynomial is expressed 1 over 2, 5x cubed minus 3x. And the P sub 4, we choose a y sub 1, n equals 4, it becomes 1 over 8, 35x to the 4th minus 30x squared plus 3. For the P sub 5, we choose a y sub 2, n equals 5, 1 over 8, 63x to the 5th minus 70x cubed plus 15x. We can create the Legendre polynomials following the same method. Then finally, I'd like to show you the graph of the Legendre polynomials. As I explained, the range of the x is between the minus 1 to the 1s. When the n equals 0, it's a constant value of the 1s. When the n equals 1, it's a y equals x. And also I show the Legendre polynomials with n equals 2, 3, 4, and 5. So you can find the Legendre polynomials. In these chapters, I introduced the two special functions Bessel functions and Legendre functions. So in the future, you might have an opportunity to study the more special functions. Basic method to find the functional form of the special functions is very similar to the method we learned today. Okay, this is the end of this session.